Hello everyone, this is Dr. Lennon, and we're going to start with the kind of more advanced integration techniques. So far presumably we've done some of the basic antiderivatives and computed some definite integrals with those, and then also looked at the substitution method. So in this video we'll look at some other basic integration techniques that apply some of these. So I've posted this table here, so that'll help you review some of them. In general, it shows us how to find antiderivatives for constants, power functions and polynomials, our trig functions that we knew derivatives for, 1 over x, and then some of the inverse trig functions. So we'll go over how these can be applied with just some algebraic techniques to find some more advanced antiderivatives, and then we'll go on from there. Again, this video is called Basic Integration Techniques, although some of these tricks you might be hard-pressed to come up with if you haven't seen them before. I've always found that a lot of the textbooks that say a brief introduction or basic, often those end up being the hardest ones. So we just want to go through a variety of examples here to show some other things that we can do involving integration. So let's go ahead and get started. So let's do our first example. So I will do a handful here, and basically we just want to find, or let's say compute each indefinite integral. So let's go ahead and start. So the first thing we want to do is change tangent into sine of x over cosine of x, just using the definition of tangent. And then from here we're going to perform a u substitution. The substitution that works here is if we let u be the cosine of x, so then du is minus sine of x times dx. So basically, well, the easiest way to do it is, like I said, we can solve for dx. So if you divide by minus sine of x on both sides, again, this is kind of typically not how I would do it. I would substitute in a different way, but it's often taught this way now just because that way you're making the appropriate substitution. So essentially, what does this integral become? This becomes, well, we can replace the cosine of x with u, and the dx we're replacing with du over the minus sine of x. So what happens is the sine of x terms cancel, and we end up just having the integral of negative 1 over u du, which we know is just going to be the natural log of the absolute value plus a constant. So we can change u back to what it originally represented, which was the cosine. So we end up with minus natural log of the absolute value of cosine of x plus a constant. So if we look back at the table, they have the natural log of the secant. So that is some very fancy algebra that they're throwing in. Typically, I would be quite happy if you just left this as the integral of minus the natural log of the cosine of x plus c. Let's say we want to write it fancy. So in terms of the table, again, they write it as this natural log of the secant. So if a were equal to 1, we would have our example. So how did they do that? Well, they used properties of the natural logarithm is what they did. So let's say using properties to make our answer look like number 14. So again, this isn't strictly necessary, but a lot of times you'll see an answer written and you'll say, well, how did they get that? Well, basically the first thing is since secant of x is equal to 1 over the cosine of x, that means that 1 over the secant of x is the same thing as the cosine of x. Okay, so the first thing we want to do is we're going to take the minus natural log of the absolute value of cosine of x plus our constant and write that as minus natural log of 1 over the secant of x plus our constant. And then we're just going to use properties of the natural logarithm that says we can take the so we can rewrite 1 over secant of x as the natural log of secant to the minus 1 of x plus our constant. And then what we can do is we can bring that exponent down in front. So we'll end up with negative 1 times the negative natural log of the secant of x plus our constant, which the two negative ones being multiplied now cancel out, and we have the natural log of the secant of x plus our constant. So this is what they have in the table above, but they just, since they're doing the integral of the tangent of ax, they end up with 1 over a tangent of ax, natural log of the secant of ax plus the constant as the antiderivative. Here we don't have the a, so we just get the natural log of the secant of x with no additional coefficients. But again, it's one of those ones where they say, okay, the antiderivative is straightforward, but there is some algebraic trickery involved. Okay, so for another even sneakier antiderivative involving some algebraic trickery, let's go ahead and compute the antiderivative of the secant of x. So the trick here is we're going to multiply by a clever form of 1, because if you multiply by 1, it doesn't change the value of the expression. Oftentimes we're just using it to change what the expression looks like, because we might see some useful trick. So the trick here, it's very hard to see unless you're expanding a bunch of derivatives for secant and tangent and looking at where those might be. But the trick is, so multiply secant of x by, so go ahead and pause your videos and try and guess the clever form of 1 if you can. If you do and you've never seen this before, that's amazing. But the clever form of 1 is secant of x plus tangent of x over secant of x plus tangent of x, right? And this expression is actually equal to 1. So what does that do for us? Let's go ahead and see. So then our integral becomes the integral of the secant of x times secant x plus tangent x over secant x plus tangent x. And we can go ahead and distribute the secant of x through the numerator. So on top we get secant squared x plus secant x tangent x, and our denominator is just secant of x plus tangent of x. And then amazingly enough, you might see the substitution now that takes place. What is that substitution going to be? Well, we know the derivative of the tangent of x is the secant squared x, and we know the derivative of secant x as secant x plus tangent, secant x tangent x. So if you let u be the secant of x plus the tangent of x, you'll get the numerator as your derivative of u. So quite amazing. So let u equal secant of x plus tangent of x. So then du is equal to secant squared x well, I'm rewriting the order. The derivative of secant is secant tangent, and the derivative of tangent is secant squared. But since addition is commutative, we can write them in any order. So I'm just writing them to match what we see above. But if you wrote it down as secant x tangent x plus secant squared x, that's equivalent. And if you notice, du is exactly what we see on top. So our integral now can be rewritten as just the integral of du, replacing the numerator and the dx over u. And we know the antiderivative of that is, again, the natural log of the absolute value of u plus a constant, and u was secant of x plus tangent of x. So that's our antiderivative. The antiderivative of the secant of x is the natural log of the absolute value of secant of x plus tangent of x plus a constant. So quite an amazing algebra trick to go ahead and get that one to work. Okay, so moving forward, let's look at some other integrals maybe that don't necessarily involve trig functions. Let's look at finding the antiderivative of the natural log of 12x over x. So again, this one is pretty easy if you actually can remember the derivative formula. So let's just recall a derivative formula. Again, for many of these, you may be able to just go up and look at the table, but to kind of help you remember where some of those formulas might come from, I'm deriving all of these kind of as we go. So let's just recall. So let's say, what is the derivative of, let's say, the natural log of kx, where k is some constant. So for this, you would use the chain rule. And a lot of people, you remember that the derivative of the natural log of x is 1 over x, but if you put that constant in the middle, there's a couple of ways to see it, actually. You could use a substitution and do a chain rule, or in fact, you could actually just use properties of logarithms. So let's use properties of logarithms, in fact. I don't know. We could do it either way. If you have the natural log of kx, properties of logarithms would say that actually we could write this, and let's just assume for now k is a positive constant so we don't get in any trouble with domain restrictions. If it's not, then you can just leave it with the x and then pull out whatever the positive value is. Anyway, we could rewrite this as the derivative of the natural log of k plus the natural log of x. And then that natural log of k is also just a constant, so it would have derivative 0, so it would just be 0 plus 1 over x, which is 1 over x. So above, you can realize now that if we let u be the entire numerator, du will be giving us the 1 over x that we need to replace the dx and the 1 over x. Just one more comment about finding the derivative of the natural log of kx. You can also do that using the chain rule, where you let u equal kx, and then the derivative of the inside is k. So you're going to get k times 1 over kx, and the k's will cancel, and you just end up with 1 over x. So you don't have to use properties of logarithm. You can also just use the good old chain rule to figure that one out. But anyway, so this is kind of what leads us, if you remember that derivative, to knowing what substitution to make. So basically what we're going to do now, so let's kind of just frame this in. We're not using that on this problem. That's just old information. So we're going to let u equal the natural log of 12x, and then du is 1 over x dx. So utilizing that substitution allows us to write the integral as the integral of u times du. and that's a very easy antiderivative. We just apply the power rule, so we get u squared over 2 plus a constant, and we can change u back into the natural log of 12x. So this is going to be the natural log of 12x squared over 2 plus a constant. And that's our antiderivative for C. For D, let's go ahead and do another one that involves a substitution, which is just a very small variation. So D, let's go ahead and look at computing the integral of, say, e to the 4x divided by e to the 4x plus 1. So kind of the problem is you'd like to be able to use a substitution here, but well, if you try the substitution, what would you want to do? You'd want to let u probably be the entire denominator. That way we can use the logarithm, right? If we see 1 over u coming out somehow, then that's going to be a very easy thing to compute. So what we'd like to do is maybe say let u equal e to the 4x plus 1, and then what will du be? Du will be equal to, well, the derivative of e to the 4x is just 4e to the 4x, and the derivative of 1 is 0, so we get 4e to the 4x dx. And again, you can go ahead and solve for dx if you want to cancel, or you can just say, well, I want to leave the e to the 4x there because that's in the numerator, so maybe it just depends on your preference. Like typically I would just divide by 4 and say, okay, e to the 4x and dx can both be replaced by du over 4. But I've seen both ways. So let me do it this way. Du over 4 is the same as e to the 4x dx. And so then our integral that we have up here can now be computed. So basically we get the du over 4, which we can just write as a 1/4 in front if we want to move our constants outside, and then the e to the 4x is replaced, so is the dx by the du, and we are left with 1 over u du. So this would just end up being 1/4 the natural log of the absolute value of u plus a constant, and we can change u back into e to the 4x plus 1 plus a constant. Again, this is just our substitution up here. So pretty straightforward there. So let's go ahead and do another. So for E here, we're going to do one that involves 2 tricks. So the integral of x plus 3 over x squared plus 16. So the first trick is not so hard. Basically what we have is we can split this fraction up using the 2 terms in the numerator. So the first trick is just using the common denominator. So this can be rewritten as the integral of x over x squared plus 16 plus the integral of 3 over x squared plus 16. Now the first integral is pretty easy to compute. We can just use a u substitution. So so how would that u substitution go? You can recognize it because if you let u be x squared plus 16, du will be basically 2x dx. So maybe I'll leave that to you, but you can try and figure out the first integral. So the first integral should be 1/2 natural log the absolute value of x squared plus 16. And then we have our other integral here. I'm just going to leave it as is. 3x squared plus 16 in the denominator, and I'll just say by u substitution, and you can go ahead and try to figure out how to do that u substitution on the first integral. The second integral is a little bit tricky to figure out, so let's go ahead and see how to do that. So So now the question is how to compute the second integral, and once we've done that, we'll have finished. So there's some algebra in there, and there's also a derivative formula we want to remember. So let's remember the derivative formula. So you might remember a derivative that looks something like the argument in here. So what would that derivative formula be? So let's recall the derivative of the arctangent or the inverse tangent. So if you take the derivative of the inverse tangent of, let's say, some algebraic expression, maybe I'll use something different than x since we're already using that. Let's say the inverse tangent of alpha. Say we're finding that derivative. It's going to be 1 over alpha squared plus 1. Okay, so that formula is going to come into play. So basically, we're going to use algebra and this derivative formula to figure out the answer to that question above. So the first thing we want to do is we want to just pull the 3 out of the integral. So we can write this as 3 times the integral of 1 over x squared plus 16 dx. And then what we're going to do is we'd like to make the bottom look something like x squared plus 1, but we've got a 16 there. So the way we can do that is we can actually factor out a 16 from the denominator. So how do we do that? We write 3 times the integral of 1 over, we want to take out a 16, so we're going to have to put a 1 over 16 in front of the x squared, so we get 1 over 16x squared plus 1. Now note that this is actually the same denominator. If you distribute the 16 to the first term, it cancels with the 1 over 16, and if you distribute it to the 1, you end up getting the same denominator of x squared plus 16. So now what I'm going to do is I'm going to replace that. I'm going to take the 16 out, so now I have a 3 over 16 outside the integral, and I'm computing the integral now of 1 over, and instead of 1 over 16x squared, I know 1 over 16 is 1 over 4 times 1 over 4. So I can write this as 1/4 x quantity squared plus 1. And then essentially I know that that is going to be giving me the, I've written that in such a form that it looks like the derivative formula for the inverse tangent that we have above. So I can complete that by performing one u substitution inside there. So I basically want to let u equal 1/4 x. So if I just do that over here, let u equal 1/4 x, then du will be 1 over 4 dx, and I'll be able to replace that integral. So just to keep everything straight, let's write 4 du is equal to dx. That way we can just replace it directly. So we'll get 3/16 times the 4 d. I'm going to write the 4 in the front of the integral, and then we get the integral of 1 over u squared plus 1 with our du. So we're almost there. The 4 and the 1 over 16 will cancel, so we can just write that as 3 over 4. And then the antiderivative of 1 over u squared plus 1 is just going to be the inverse tangent of u plus our constant. So this ends up, we can replace our u now by the 1/4 x plus a constant. Okay, so that is the antiderivative to the integral in question. So maybe what we can do is we can come back up top and say, so we had a lot of work there. So if we call this right here equation star, so sorry, kind of getting a little. So replacing this expression in star, we have, so what was the original integral? We had the integral of x plus 3 over x squared plus 16 dx. This is actually now equal to our antiderivative, which the first term I believe was 1/2 natural log of the absolute value of x squared plus 16. That was the first term. And then the second term here is plus that 3/4 inverse tangent of 1/4 x, or x over 4 if you want to write it as a single fraction, plus a constant. So that was quite a problem. We started by having a split using common denominators. Then we performed a u substitution on the first part of the integral, and then the second part of the integral we used a u substitution along with the antiderivative formula for the inverse tangent of x. So that should give you quite a lot to think about reviewing that problem. So let's try and do a couple of more, maybe 2 more examples. So this was a long one, E. Yeah, so now we're on part F. So let's integrate, let's say 1 over x squared minus 2x plus 37 dx. So the trick here for this example is completing the square. So you might remember it from algebra. So how does completing the square go? Well, if you have x squared plus bx, and you add b over 2 quantity squared to it, this will always factor into x plus b over 2 quantity squared. So in the above example, we could look at the first 2 terms of the denominator. So x squared minus 2x, if we could write that somehow, if we could add a term to it, what we'd want to add is we'd want to add 1, because x squared minus 2x plus 1 would factor into x minus 1 quantity squared. Right? B is -2, so -2 divided by 2 squared is plus 1. And that's actually not so difficult to do, because we can take the integral and just write it as the integral of 1 over x squared minus 2x, and we can write 37 as plus 1 plus 36. And then that's nice because we've now factored, or we're now able to factor the first 3 terms, that trinomial on the bottom. So we'll have x minus 1 quantity squared plus 36 squared, which we can write as 6 squared dx. And again, this is going to basically fall back to an inverse tangent type of situation that we had last example. So let's go ahead and find that in the table and just use the table instead of going through the inverse tangent argument again. So what did that relate to in the table? Well, if you have dx of a squared plus x squared, it's 1 over a inverse tangent of x over a plus c. So we're going to be using integration formula number 11 for part F down here. The problem is we currently have it as x minus 1, so we'll have to do one little u substitution, but it won't amount to much, because what we're going to do is we're just going to let u equal x minus 1, so du will equal dx. So this actually just becomes the integral of 1 over u squared plus 6 squared dx, du, and then we apply the integration formula. So this will now equal 1 over 6 times the inverse tangent of, was it 6u then? So let's recall. So basically if we have the a squared plus x squared, a is 6 in our example, so we're going to get 1 over 6 inverse tangent of x over 6 plus the constant. In this case, we're not using x, we're using u, so we are going to have to substitute back. So all the way back to the bottom. So 1 over 6 inverse tangent of u over 6 plus a constant. This is by integration formula number 11 in the above table. And again, if you go back through the last steps of the previous example, we showed you how you can actually derive that by hand. And then what we want to do is just change u back into x minus 1. So this is 1/6 the inverse tangent of x minus 1 over 6 plus a constant value. And that's it for this problem. So this one is applying the inverse tangent formula, which was number 11 above, along with the idea of completing the square. So for our last example, let's go ahead and look at one that involves the idea of multiplying by the conjugate. So we'll call this example G. So we want to compute the integral of 42 over 1 minus the cosine of 6x dx. And the trick in this example is we want to multiply by the conjugate. So basically what that means is if you have some expression a plus b, you can multiply it by an expression a minus b, and you get a squared minus b squared. That's going to be helpful with trigonometric identities, because if you have something like the cosine and you multiply 1 minus cosine and you multiply it by something like 1 plus the cosine, you end up with 1 plus cosine squared, or 1 minus cosine squared, and then you'll be allowed to apply the Pythagorean identity to rewrite it. So that's what we're going to do here. So we're not only multiplying by the conjugate, we're doing it in terms of the clever form of 1. So basically, in the above example, we want to multiply by 1 plus the cosine of 6x over 1 plus the cosine of 6x. Again, that is a clever form of 1, so we're not changing the value of the expression that we're actually trying to integrate. So we have the integral of 42 over 1 minus the cosine of 6x, and we're multiplying by 1 plus the cosine of 6x over 1 plus the cosine of 6x. So the bottom is going to become 1 minus the cosine squared of 6x. And the top you can distribute, so or you can pull it out of the integral. It's honestly up to you. So for now, let's just pull it out of the integral. So let's say we have 42 times the integral of 1 plus the cosine of 6x. And on bottom, we now have 1 minus the cosine squared of 6x. And now we can replace the denominator. We can replace 1 minus cosine squared of 6x as sine squared of 6x. That is just the Pythagorean identity. So 1 plus the cosine of 6x over sine squared of 6x. So this is by the Pythagorean identity. And then we can go back to rewriting the thing that we're integrating using the common denominator to split that up. So we have 42 times the integral of 1 over sine squared of 6x dx plus 42 times the integral of cosine of 6x over sine squared of 6x dx. So using some further trig identities, 1 over sine is the cosecant, so the first integral here can be rewritten as 42 times the integral of the cosecant squared of 6x dx. And the second integral can be rewritten as 42 times the integral of, well, we'll have cosine over sine, which is the cotangent, and then we'll also have a 1 over sine, which is cosecant. So we'll have cosecant 6x times cotangent 6x dx. And again, we have some basic integration formulas for those above. We know the antiderivative. So again, both of these are going to have a little u substitution in them because we want to let u be 6x. So we can do that with both integrals. So let u equal 6x. So then du is equal to 6 dx. So du over 6 is the value of dx. So basically the 1/6 from the substitution is going to come out front, and that will cancel with the 42, right? 42 divided by 6 is 7. So we can rewrite these integrals now using the u substitution. So we have 7 times the integral of cosecant squared u dx plus 7 integral of cosecant u cotangent of u du. And those are both basic integration formulas. So remember that the derivative of tangent was secant squared, so the negative derivative of cotangent is cosecant squared, so this is going to come out to minus 7 cotangent u, and the derivative of cosecant is cosecant cotangent minus cosecant cotangent, so this comes out to minus 7 cosecant u plus a constant, and then there's just one last step to change that u back to 6x. So this finishes off as minus 7 cotangent of 6x minus 7 cosecant of 6x plus a constant. And that's it. Again, the trig ones can often get a little complicated, but I tried to include ones that had all the mess so that you can walk through how to involve the constants on the inside and things like that. And again, probably both of these are mentioned in the integration formulas up top, so maybe you can do them directly instead of appealing to doing everything by hand, deriving it. Let's see if there was one like that in the table. So we had the cosecant cotangent is formula 8. That's going to be minus 1 over a cosecant of ax. Again, our 1 over 6 that was coming out was canceling with the 42, so that's why we don't see that. And for the cosecant squared, we have that from the minus cotangent, so that's formula 6. So in that last problem G, you could have done those just appealing to formulas number 6 and number 8. which is basically what we did. Anyway, those are some of the more complicated ones. From here on out, we'll move on to integration by parts next. Anyway, this is Dr. Lennon signing off.